So, welcome back to this class on hardware security. So, we shall continue our discussions on the linear feedback shift register and its resistance against power attacks. So, we shall be trying to discuss about power attacks of LFSRs and continue our discussion on the standard stream cipher, which is called as MIKI. So, we basically stopped at this point where we were reflecting on the whether the Fibonacci LFSR is more vulnerable against power attacks compared to the Galois LFSRs. Okay. So, let us try to analyze the Fibonacci LFSR. Okay. So, here we basically see that the Hamming distance or HDT that we have defined is the Hamming distance between two consecutive states of the LFSR at time t. Okay. So, it turns out that we have defined a parameter called PDT, and which is nothing but the difference of consecutive HDTs, and this PDT, if I denote it as HDT plus 1 minus HDT. Okay. So, the idea is that this value can either be like minus 1, 0 or plus 1. Okay. So, if you remember right in the last class, we basically defined PD dash. Okay. So, PD dash was the fact that if the power consumption remains same or whether the power consumption differs. Okay. So, here you can see that the power consumption can remain same in one of the cases out of 3 cases, whereas the power consumption can differ in 2 cases out of the 3 cases. Like when the PDT is minus 1, there is a difference in power consumption, because PDT minus 1 which means that HDT plus 1 was 1 more than HDT, okay, and that is why this value got minus 1, and therefore, there is a change across clock cycles in the power consumption. Likewise, when PDT is 1, that also implies that the power consumption is increased. Okay. So, in both cases, like in one case there is a decrease, one case there is an increase, but that means that there is been a change of power consumption. So, in order for the attack to work on real traces, what we just need is to be able to distinguish from the fact that whether the power consumption has increased or the whether the power consumption has remained the same or the power consumption has changed. Okay. So, in this case, right, the PDT value is minus 1, 0 and plus 1. Okay, and this you can easily understand. So, let us try to reflect on why this is so. Okay. So, and that is pretty simple in context to the Fibonacci LFSR. Okay. So, in the Fibonacci LFSR, remember that you have this state, right. So, the state, let us write it as like Sn minus 1, Sn minus 2, so on till S0. So, this is your LFSR state, and you basically, what you are basically trying to do is you are calculating Sn, which is your feedback value. Okay. And this feedback value depends upon certain tap positions which you are taking from here, and you have got this feedback polynomial. So, this is your feedback polynomial, which is nothing but having some XORs, and then you basically calculate the value of Sn. Okay. So, that means, right, I can write the value of, say, like let us denote this state as St and the corresponding time instance by the suffix t. Okay. Then that means that STT is this value, right, is basically Sn minus 1, Sn minus 2, so on till S0. Okay. In the next time instance, you have got STT plus 1. So, in STT plus 1, what will happen is that this Sn will get into the register. So, you will be Sn, comma, and this will get shifted. So, you will have Sn minus 1 and so on, this will continue till S1. Okay. Likewise, in the next time instance, you will have STT plus 2, and this is nothing but Sn plus 1, comma Sn, and comma this will continue till S2. Okay. So, therefore, right from here we can calculate the value of HDT, right, and what is the value of HDT, as we have discussed, right, is nothing but the Hamming weight, because it is the Hamming distance between those two parameters. It is the Hamming weight of Sn minus 1 XORed with Sn. Okay. So, that means these two things are XORed. Okay. Likewise, I will XOR these two. Okay. So, it is Sn minus 2 XORed with Sn minus 1. Okay. And likewise, finally, I have got an S0 XORed with S1. Okay. Likewise, if I want to calculate HDT plus 1, then HDT plus 1 is nothing but the Hamming weight of, I will be now considering the Hamming weight means these are the two things that I will be XORing now. So, I will have here Sn XORed with Sn plus 1, okay, and then again I will be XORing these two. So, it will be Sn minus 1 XORed with Sn, okay, and like this, right, I will be XORing these two. So, it is S1 XORed with S2. Okay. So, now the definition of PDT is nothing but HDT minus HDT plus 1. Okay. And you can observe that here among all these terms, you can see that this term matches with this term. Okay. And likewise, if you had observed the previous term to this, right, it should have been S1 XORed of S2. So, this also would have matched with this one. Okay. So, therefore, the new term that is over here is one of them is this and the other one, right, is this. Okay. So, therefore, this difference would be nothing but the Hamming weight of S0 or like S0 XORed of S1, okay, minus the Hamming weight of Sn XORed with Sn plus 1. Okay. So, note because these are the two things which are only different, and therefore, right, the final result will depend on the difference between these two. So, this Hamming weight, right, since is the Hamming XORed of only 1 bit values, this can be either 0 or 1, and likewise this also can be either 0 or 1, and therefore, when I take the difference, then the difference can be either minus 1, 0 or plus 1. Okay. And that is why, right, you have got 3 levels, I would say here, but out of which, right, 2 are where there is a difference, okay, and there is one case where there is no difference. That means the power essentially remains constant. Okay. And therefore, right, in this case, right, we will have the PD dash value as 1, whereas in this case, right, your PD dash value will be 0 because there is no difference. Okay. So, now you see that the power of my attack depends on my ability of correctly calculating this PD dash, okay, which means of being correctly distinguishing this non-zero difference from this 0 difference. Okay. So, that means from the non-zero difference from the the non-zero difference from the 0 difference. Okay. So, that implies that if, right, for example, if I have in this case, right, since there are only 2 non-zero differences compared to 1 0 difference, we will now compare this with the Galois LFSR, okay, and we will see that the the PD dash values, the PDT value there can take more levels, okay, and that essentially will be my the base of the argument or base of my comparison between these two configurations. So, let us see how this PD value looks like in the when we are in particular comparing and finding out the same stuff for the Galois LFSR. So, in Galois LFSR, if your number of taps is n, and for an LFSR with primitive connection polynomial, then n is even, okay. And in that case, again, if I define PD dash in a similar way, we can argue that the PDT dash, the PDT value can have more levels, okay. So, it can, for example, have levels, of course, it will have some 0 values, but there are more non-zero values, like it can have minus 1 to minus n minus 1, and likewise it can have from 1 to plus n minus 1, okay. So, that implies that in a similar way, if you observe, right, then so likewise, right, in this case, if I take the PDT value and find out the 0 difference case, right, in the 0 difference there is one case, because this is your 0 difference case, whereas there are many non-zero difference levels, okay. And the non-zero difference levels also observe that for example, it can go as high as up to n minus 1, okay. So, which means although so if you are doing this attack on real power traces, then you can intuitively understand that it will be hard for you to distinguish these cases because they are almost close, okay. Whereas, if you have got some jumps which are as high as this, then they are more discernible, they are more distinguishable from this 0 level, okay. And you can see more more details on this derivation in this reference which has been shown here, which is essentially a paper which was published in Space in 2014, which talks about Fibonacci LFSR versus Galois LFSR, which is more vulnerable to power attack. So you can see the derivation of this particular result. Okay, but at this point, right, what is just important for us is to know this fact that in a Galois LFSR there are more jumps which are possible. Okay, the PDT value can simply take more levels. Okay, so what is the implication of this? So therefore, right, when you are trying to attack the LFSR configurations for both the LFSR conditions, right, the PDT value equal to 0 when HDT equal to HDT plus 1, else the PDT is a non-zero value. And if the PD sequencer correctly retrieved from real power traces, then the initial state, the secret key of the LFSR can be completely determined using Berlekamp-Massey algorithm, as we have already discussed. So therefore, right, this forms the basis of our comparison between these two configurations. To retrieve the PD sequences correctly, we need to implement a thresholding operation on the real power traces, because in real power traces you have to have a proper threshold to tell that this is like a zero difference and this is a non-zero difference. Okay, because you will have real values in the power trace. So more the difference between a zero and non-zero level, therefore better will be your the result of thresholding, and because the effect of noise will be less in such case. You will have a high you will have a better distinguishing power. So as we have seen that in case of Fibonacci LFSR, the magnitude of non-zero values is only 1, okay, which means the zero state, the zero difference and the non-zero difference are very close to each other. On the other hand, in a Galois LFSR, the magnitudes of non-zero values is very large. It can go as high as n-1, okay, so it is pretty large. So therefore, right, it is clear that the difference between 0 and non-zero levels of PD sequences is higher in the Galois LFSR than its Fibonacci counterpart, okay, as we have seen that the gap is much wider in the Galois LFSR, and therefore, right, there is a higher distinction possible in the case of Galois LFSR between the two levels, and this implies that the effect of low SNR power sample points is less. Okay, that means the effect of noise will be less in the case of Galois LFSR, because remember that if there is a noise on top of it, right, then there is a quite high chance that the 0 and the 1 difference will get blurred. Okay, whereas, right, if you have got large differences possible, as we can see that is possible in the case of the Galois LFSRs, then the effect of noise will be less. Okay, so therefore, right, we can conclude that the Galois LFSR configuration is more vulnerable to power attacks compared to the Fibonacci counterpart. You can also experimentally observe this. So this is an example of an attack which has been done on the Fibonacci LFSR, shown by the grey color compared with the blue color, which talks about the Galois LFSR. And we have done several instances of in the attack is shown in this graph, and you can see that in almost all the cases for the Galois LFSR, the correct percentage of retrieval of the PD sequences is higher. Okay, so this bar shows like the correct percentage of the retrieval of the PD sequences, and as you can observe that the retrieval rate is higher in case of higher in case of the Galois LFSRs, and that is also expected from the theory that we just discussed. Okay. So now with this background, right, it basically tells us that even stream ciphers like block ciphers are also vulnerable against power attacks or DPA attacks. Let us try to see, like if I try to apply a DPA on an actual stream cipher. Okay, so in an actual stream cipher, right, you will not have only like one single register, but maybe you will have much more registers. Okay, so Mickey, or what it stands for, so Mickey was essentially a stream cipher which was designed by Babbage and Dodd, and it was selected as one of the 3 hardware-oriented algorithms in the final portfolio of eStream, which was a movement to like find or to basically standardize stream ciphers. So the stream cipher Mickey, which stands for Mutual Irregular Clocking Key Stream Generator, is aimed at resource constrained hardware platforms, and it is intended to have a low complexity in hardware while providing a high level of security. In fact, Mickey 2 and Mickey 128.2.0 have got security levels of 80 bits and even as high as 128 bits respectively. So this is how the Mickey looks like. You can see that there are 2 registers, register R, which is a linear feedback shift register, and register S, which is a nonlinear feedback shift register. and there is a control for independent control for the register R and for the register S. Okay, so that means the feedback essentially, or the clocking of both the LFSRs is essentially takes place in a somewhat irregular way, and that is why its name. Okay, and they are finally XORed to get your key stream bits. This is the corresponding output of your key stream generator. But there is, so there are different stages of how of this particular LFSR works. So as I said that MICI 128 2.0 takes two input parameters. It takes a 128 bit secret key K. It also takes an initialization vector, which is a public information, which is between 0 and 128 bits in length. The ciphertext is produced from the plain text by bitwise XORing between the key stream bits, and as we have seen, right, in most stream ciphers, that this is the output bit. Like when you take this key stream bit, you XOR it with the message bits, and you get your corresponding ciphertext bit. Okay. So the generator is now, as we have seen in the picture, is built from two registers, register R and register S. Both of these registers are 160 bits long. Okay, and each stage containing one bit. And broadly speaking, you can think of R as a linear register, whereas S is essentially a non-linear register. Okay. So this is how the MICI architecture looks like, and you can see that the register R and the register S are essentially updated, and like the input bit is shown here as input bit R, and this is the input bit S, and there are two tap positions which I am basically taking from the register R and the register S, and we are XORing it to get the key stream, which is XORed with your message. Now there is an important point in this architecture, like you can see this is the input bit. Okay, so this input bit is basically like mixed in depending upon this select line which is mixing. Okay, so this mixing, as we will see, right, is initially kind of disabled. Okay, so I mean rather like you basically initially would like to like initially you have to load in there are two parameters that you have to load, the initialization vector and the key, which are done in two specific stages of the stream cipher. Okay, so let us see how essentially we do that. So first we clock. So let us see about the clocking of the registers R and S. Okay, so the first thing that we see is that how we clock register R. So in register R, right, there are, as you can see, the parameters are R input bit R and the control bit R. The idea is that so R0 to R159 are the states of the register R before clocking. And after you have done the clocking, right, they are denoted as R0 dash to R59 dash. Note that they are 160 bits in length. The feedback bit, as we have seen, right, is calculated by XORing of R59 with this input bit R signal. Okay, so that means, right, you are either toggling R159 or you are basically passing R59 as it is. And then this is the evolution of the shift register. As you can see that from 1 to 59, I am just shifting. Okay, and then what we do is we basically calculate the value of Ri dash again. Like you basically take in the feedback bit and you XOR it with the corresponding Ri dash values. And if the control bit R is 1, then you basically XOR Ri dash with Ri, Ri dash with Ri, and you get the value of Ri dash. Okay. So likewise, right, you can also like you can go into the specifics, but essentially there is another way in which you are clocking register S. So you are basically independent clockings of register R and clockings of register S. The point, one point which you can probably see over here is that there is in the feedback over here there is an AND gate which has been used. This AND, if you see, like if like now this AND essentially is one of the reasons why we call this register S as a nonlinear feedback shift register. Okay. So basically you update the register R and the register S through these algorithms, and then you clock the overall generator in this way. So you basically if you set your mixing as true, then you basically clock your R and you clock your S by by these equations. So you can see that here I take my input bit R and I just XOR the input and I obtain it by XORing input bit with S80, which is one of the states which I am deriving from S. So you can see that it's a very interesting way of updating the clocks, because now register R is being mixed with the state of register S. Okay, and that is happening because mixing is said to be true. Okay. On the other hand, right, you can see that the clock S essentially where you are updating state S, you are like mixing in you're basically in this case, right, the clock S is independently processed. So you basically just take the input bit S and you initialize it to input, or you basically assign it input underscore bit to input underscore bit underscore S. Okay. On the other hand, right, if you are setting mixing to false, then register R works independently. So therefore, this particular XOR is not present when you are updating, say, clock underscore R. Okay. So now you can observe that as I said, that initially there is a phase when you are uploading the you are loading the key and you are loading the initialization vector. So first you load in the IV and then you load in key, okay, K, and then you do a pre-clock session, and then after that you start your key stream generation. Okay, so you can see that in all these states, right, mixing has been set to true, which means since mixing is true, the clock register R is updated by this equation. And finally, right, when you are generating the key stream, at that point mixing is set to false, and therefore you are just using this to generate the you are just using it to generate your key stream, which you are XORing with the message to get the ciphertext bits. Okay, so therefore here is so that's the more or less working of the Mickey stream cipher. And Mickey was essentially very popular, in particular when we discuss about hardware design. So you can see here, this is the result of the footprint of hardware implementation of Mickey compared to some other potential candidates like Trivium and so on. And you can see that Mickey essentially stands out by taking quite small amount of area in terms of resources. Okay, but so here is but as we can see, right, that as in most algorithms or most cryptographic algorithms, it also is vulnerable against power attacks. Okay. So in order to see that, we basically observe, as in the first step, we basically put it in our setup for doing power trace acquisition, and here you can see how the power trace of Mickey looks like. So these are the various samples that has been observed, and this is the power consumption. You can see there is a distinct nature of the power traces, and that is expected from the the evolution of the stream cipher. So this has been acquired on a Sasebo G2 board. Okay, and in the second step, we basically try to develop the attack. So as very important, right, I mean in DPA, as we have seen even in the context of block ciphers, you need to make a target position. Okay, so the basic idea is that you basically build your hypothetical power consumption matrix by a power model. So this could be a Hamming weight or Hamming distance power model, and the basic idea is to look for intermediate values which can reflect the power consumptions effectively. Okay. And then you choose a proper power model. So what we do in our case is basically we target the register R and the register S, and we try to find out the kind of the summation of the register R content and the register S content, and we find out the Hamming weight of that essentially as your power model. So then we attack. So when do we attack? Okay, so as we have seen that in the stream cipher there are different phases of the stream cipher. In particular, we basically target the phase where we are uploading the key. Okay, as you can see that the key bits are uploaded one by one, and we basically do that. So we basically keep the key fixed, and we kind of vary the initialization vector, and that is and we specifically target the content of register R and register S to derive your hypothetical power, and then we kind of match this hypothetical power or correlate this hypothetical power with the real power which has been observed by our observations. Okay, that is from your side channel acquisition. So that is done in the third step, where we basically try to correlate and basically apply like correlation power analysis, and we recover the key bit by bit. Okay, that means you basically load the key bit can be 1, you basically guess the key bit can be 1, can be 0, and then you do a CP attack and try to kind of confirm whether your guess was correct or whether your guess was wrong. Okay, the idea is that if your guess was correct, if your key bit was correctly guessed, then the hypothetical power, that means the content of the register R and the content of the register S, will correlate very highly with the actual observed power, whereas if your guess was wrong, that means if your key bit was wrongly guessed, then your correlation will be small, and therefore you can distinguish between these two cases to discard the wrong guesses and correctly know the key in a bit by bit fashion. Okay. So here are some experimental results that you can observe. Like this, for example, when the key bit 16 is being tried to be recovered. Understand that when you are trying to recover key bit 16, then I am assuming that from key bit 0 to key bit 15 has already been recovered. Okay, and I am just guessing the key bit 16. I am making a guess either 0 or 1. in this case, right, the correct bit is 0 and it is shown in blue, and you can see that blue is below. Okay. So, one of the reasons, right, I take the one which is below is because, you know, like I get a negative dip in my power consumption, okay, and therefore, I basically observe the negative correlation, okay, but something which correlates more in the negative direction. Okay. In this particular graph, 0 is at this point. So, you can find out 0 essentially this is this line. Okay. So, 0 is this line, that means, right, I observe that since 0 is this line, the blue line, that is the one which corresponds to the correct key bit, essentially is correlating more compared to the red lines, which are essentially are more at the top. Okay. And therefore, right, we basically can correctly determine that the correct bit is 0. You can do similar analysis at different positions. For example, this is again when we have increased the number of power traces. So, in the previous case, the number of power traces was 100. Here the number of power traces is made to be 500, and here you can see that the peaks in the negative direction are even more, and they are therefore more distinguishable from the wrong guess. Okay. You can, so this is an example again when we are increasing further the number of traces, you can see that the negative direction correlations are increasing further, and therefore they are more distinguishable. Okay. So, you can similarly target at other key bit positions. So, this is the scenario when key bit 14 is being targeted. So, in this case 0 till 13 are already been recovered, and I am just guessing key bit 14, and you can observe that again there is a similar, you know, like distinction which is being done, and you can observe that there is an amount of separation which you get with 100 power traces. Okay. But here it is not so distinguishable, as you can observe, right, because the red and the blue are kind of quite intertwined. Okay. So, now what happens is when I am increasing the number of power traces, in this case I see the separation is quite nice. Okay. So, you can see that this is the, so in this case the correct key bit is shown by the red color, and you can see that there is a more negative correlation, right, which is what we are expecting here, and therefore, we can correctly say that the correct bit in this case is 1. Okay. So, so this is shown in the red color here. If you are taking 1000 traces, the separation is even more. Okay. So, we can make some remarks about the attack is that in our experimental setup, higher power consumption corresponds to a dip in the negative direction, okay, and that can happen in your setup. So, depending upon that, you have to look for correlations either in the positive direction or in the negative direction. So, therefore, in our case, we look for negative peaks to predict the correct key bit value. The nature of the correlation plot varies from bit to bit. Okay. In some cases, only 500 traces are quite good enough. In some cases, right, we find out that probably we need more, and in what we found out is that around 1000 traces are found to be sufficient to get the complete retrieval of, I mean, to get the retrieval done, or to get the retrieval be successful in all the possible bit positions. Okay. So, here are some references which we have followed from the book, okay, I mean which we have followed for this discussion. In particular, right, this reference 3 is the paper that I referred when I was talking about the linear feedback shift register, that is the Fibonacci LFSR in particular, whereas there are some other references which essentially talks about power attacks on stream ciphers. For example, this second reference is on a power analysis attack on hardware implementations of the stream cipher Mickey, which we kind of redid and exhibited here. Okay. So, so therefore, right, to conclude, what we discussed is that LFSRs are vulnerable to DPA. In particular, Fibonacci and Galois LFSRs are not equivalent with respect to power attacks vulnerabilities, although theoretically they are isomorphic to each other, but they are not so when we consider power attacks, and we found out that the Galois LFSRs are more vulnerable to DPA because there are more separations, right, there are more levels of jumps which are possible in the Galois LFSR, and and therefore they are more vulnerable to a power attack. In particular, we also discussed that DPA can be adapted and applied iteratively to retrieve the key bits of stream ciphers. We showed it by an example of Mickey, but pretty much this idea could be extended to other stream ciphers like Grain, Trivium, and so on. Okay. So, with that, we would like to come to an end to this class, and thank you for your attention.